What I want to do last is I want to talk about inelastic collisions. So now let's look at inelastic collisions. Inelastic collisions falls into two categories. Let me bring this up here. So there are two categories that break up this class of collisions. Now, typically it shouldn't be broken up, but it is. So when they say, so this is, the wording's a little bit slippery here. So when I say the word inelastic collisions, I'm going to say that there are inelastic collisions, which sounds kind of crazy. There is an inelastic collision. And then the second kind, not the kind, but a category, they break it up to in what is called completely inelastic collision. And what you're going to find here is that I want to try to draw two pictures because you somehow have to be able to separate these two. And they're fine to separate, they're easy enough to separate. So how do I want to separate these guys? So the first thing that I would do here is that I would go back to what we talked about in the past. And what we did here is that we talked about what happens in collisions. And one of the things that we said here is that if I have a elastic collision, this is a perfect collision that creates no sound or generates any heat. Those are perfect collisions. So a very, very good example of a perfect collision here is that I can take a ball and what happens is that I'm going to drop this ball. So as I drop this ball, I'm doing that at an angle so that it's easier to see. And so what I'm looking at it is that right before it hits the ground, it now is coming. Remember, it's still going straight down. It has this momentum coming in. And then right afterwards, right, this is the before and after the collision here. It has momentum that is coming up like this. You know what? Let's not do initial. Let's just do P1 and P2. And what happens here is that the ball comes up to the exact same height. So a perfect collision, so it drops, bounces, and returns to original height. You see it hit the ground, but it doesn't make any noise. I mean, think about that. If you drop a golf ball, you know you're going to hear a sound. But there's no noise, there's no heat that's generated. In inelastic collision, this does create sound and generates heat. And so what you're finding here is that in the previous case, what you're seeing here is that all the energy goes into motion in this case. And in this situation, what you're going to find here is that some of the energy goes into sound, heat, and everything else, deformation of the object, whatever that is. And so what you're seeing in this situation, that when you drop the ball and it does hit the ground, so when I look at that momentum right before here, I look at this momentum 1. So by the way, in this situation, before and after the collision, which I did not state, this essentially tells me that the momentum of 1 is the same as the momentum of 2. But in this situation, what you're going to find here is that there is momentum transfer elsewhere. In other words, when I look at this momentum, these momentums are not the same anymore. And the clearest thing here is that you can see here that there is a height change. And so therefore, there is sound, and the collision generates heat on the ground and also on the ball. This is an elastic collision. Inelastic collisions are usually the hardest to identify. One must do a calculation to check if energy is used elsewhere. And typically, when we say the word energy, we really mean this term called kinetic energy. And kinetic energy is the energy of motion. But that's not part of this chapter. It's the next chapter. So again, this is one of the toughest ones. So this is something that we will not be able to do in this course. So which is most likely the case? So if I have an inelastic collision, we typically, so if we have an inelastic collision, it will most likely be completely inelastic. So what do I mean by completely inelastic? I mean this. What you find here is that two objects stick together after the collision. So a good picture would be something like this here. So as an example, you could imagine that we shoot a bullet into a block. So I imagine that I have a bullet, right? Here's my bullet. And I'm shooting this with some initial momentum. Then what I'm finding here is that I have a big block right here. A big block of, let's say, wood. So this would be my block of wood. And I'm going to say that this guy starts off with some initial momentum of 0. So then what happens afterwards? What happens afterwards is that the block, or excuse me, the bullet gets embedded into the block of wood. It doesn't go all the way through. It now is stuck inside the wood. And what happens is that these guys now move together with some final momentum, where it's really the momentum of the bullet plus the momentum of the block afterwards. Let me be careful here. So now it's really the mass of the bullet plus the mass of the block moving with some final speed. This is a completely inelastic situation. So that being the case, let's go to the next example. And this is the last example of the chapter. So here's what we have. In this situation, we have a 300-gram bird flying along at 6 meters per second, sees a 10-gram insect heading straight toward it with the speed of 30 meters a second. The bird opens its mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing? Oh boy, these pictures. I'm not sure if I really like these pictures here. Well, let's see you try to draw a picture of this. See if you could draw a picture of the situation. Draw me a bar diagram. What would we expect? Okay. And I'm going to try to draw a picture of the situation. Oh, man. Mm. Okay, let's get started here. So I could imagine now, actually, I should probably paint the bug so we know. So now the bird has swallowed the bug. So it now keeps its beak shut. And then the bug is right here, inside here. So let's think about this a little bit. So what do I expect to happen? Okay. What I expect to happen here is that I have a flying bird. And I have a flying bug. So beforehand, they are headed towards each other. So what would I expect here? So physically, I expect the bird's initial momentum to be larger than the bug's. So why would I expect that? So the question is why? When the bird eats the bug, does oops, does the bird continue flying in the forward direction? And my guess here, right, this is my guess, is the answer is absolutely yes. It has to. So then what I would expect here is that the final momentum of the system here afterwards is going to continue flying to the right. Now, if the bird was flying backwards after the collision, then the momentum of the bug would be higher than the bird. And the question is, is the bird okay after the collision? I don't know the answer here. So then, here I go. There's my system. Are there any external impulses to the system? And the answer is no. So then if I start looking at my bar diagram, what am I expecting here? I would expect then that what will happen here is that I have a momentum of the bird. And I expect the momentum of the bird to be higher, right? So maybe I should be painting my bird green here. But what I see here is that if I make this my positive direction and I make this my negative direction, I could see that the bug is now going negative. So what would I expect? I would expect that the momentum of the bug is small. Is that a good assumption? I think so. We'll look at the numbers here. So if I look at the momentum of the bug, I'm going to say that it's tiny compared to the bird, and it's going in the opposite direction here. So that means here that if I look at the total momentum of the system, this is the conservation of momentum line. So then afterwards, the total momentum of this system now has to be this much. So this is the momentum of going forward right here. That's what I expect. We should calculate these numbers to find out and just see if that's exactly what we expect. I would expect that the momentum of the bird afterwards is going to be lower than what it initially started with. So let's go calculate these. So then our mathematical equation follows this picture. It says that P1 initial minus P2 initial has to equal P final. And this P final now, as you can see here, I still have my bird here. And I tried to draw the bird with wings, showing you that it's still moving to the right here. And you could see here is that now, not only does it have the mass of the bird, but it has the mass of the bug too. And they're moving forward in the positive direction. So here we go. So actually, let's do it the reversed here. So the question here, what's the final speed of bird bug system? The final speed is VF. So what am I going to do? I'm going to solve for VF. So if I do that, then I'm going to use conservation of momentum exactly like it's shown here. And it says here that I now have PF, which we've already written like this. And then this guy's going to be P1 initial minus P2 initial, which then means that this will be M1 V1 initial minus M2 V2 initial. So now if I want to solve for VF, right, this is what we're solving for. I got to divide both sides by the mass. So then that tells me that VF is then going to be M1 V1 initial minus M2 V2 initial divided by M1 plus M2. So now let's look at our numbers here. So what do I know? I know that the mass of the bird is 300 grams, which will be 0.3 kilograms. I know its initial speed here, they tell us, is 6 meters a second. Now, if I focus on the bug has a mass of 10 grams. So this is 10 grams. So then this is going to be 0.010 grams. And then it tells us that its speed is 30 meters a second. It's 30 meters a second. Note, no minus sign. Why not? Because I put my minus on when I drew the bar diagram. So now I'm just going to plug in all my numbers. So if I plug in all my numbers, you could see here that this is going to be 0.3 kilograms times 6 meters per second minus 0.01 kilograms times 30 meters a second. And then I'm going to add the quantity 0.3 plus 0.01 kilograms. And then the final speed that I get here is 4.8 meters per second for V final. So that tells me the speed of the bird. So once again here, that's how you would solve it mathematically and the way you should do it on quizzes. But what about physically? Why does the bird not move backwards after the collision? Well, one of the things that you could say is look at the speed of the bird. If I look at the speed of the bird, it's 6 meters a second, but the bug speed is 30 meters a second. It's traveling much faster. It's traveling 5 times faster. But we don't care about speed. We care about momentum. So now let's look at the momentum of the bird. So if I calculate this, look at the numbers that I get here. So in this situation, here's what I'm looking at right here. Well, the mass of the bird is 0.3 kilograms times 6 meters a second. So if I multiply these out, this is going to give me, right, that's got to be 1.8 Newton second. And if I look at the momentum of the bug, even though it's going faster, its mass is much smaller here. Right? Wait, let me make sure that in my head I'm getting some funky numbers. This is going to be 0.3 like that. So what you're seeing here is that the momentum of the bird is greater than the momentum of the bug. So if I was to then put my numbers here in here, you could see here is that this is 1.8 Newton second, and this is equal to 0.3 Newton second. So if you want to stop the bird in its place, you see, you'd have to increase the momentum of the bug. So it has to go considerably faster. But that's the reason why the bird didn't move backwards.